today's program. Economical storm shelter design prototypes. This is our description and our learning objectives. Our provider statement as required. Certificate of completion will be sent to everyone that attends today. Our giveaways, you'll see a little plastic box coming around. Put your business card or just put your name on a piece of paper in the box, and we'll be giving away some ICC 500s.
Woo-hoo.
And our awesome sponsor today is Grant Masonry Contracting, celebrating 78 years actually, and 3 generations of masonry excellence. The services are commercial, institutional, industrial masonry, brick, block, stone. Grant has been an active member and an industry leader in the masonry construction industry who values the opportunity to engage in the industry, influencing the future with their expertise. Do we have anybody from Grant Contracting here? Brian Grant, Brad Grant?
Nope.
No, but we certainly appreciate them for their refreshments.
Yes.
Thank you. Thank you. So today's speaker is Darrell McMillian. He is a registered professional engineer with the state of Missouri. He graduated from the Missouri University of Science and Technology with a BS in civil engineering.
A lot of BS.
He is a member of the Structural Engineers Association of Kansas and Missouri and is a past St. Louis chapter president. Darrell co-chairs the Structural Design Task Group, the Masonry Alliance for Codes and Standards, and holds a membership with the American Society of Civil Engineers, Structural Engineering Institute, American Society of Testing and Materials. He is past president of the TMS and is a voting member of the TMS 402-602 Design and Seismic Subcommittees and the TMS 402-602 Main Committee. Darrell served as the technical director for the Masonry Institute of St. Louis from 2001 to 2023. He also has taught the structural masonry design course at Missouri S&T since 2011. Please give a warm welcome for our very dear Darrell McMillian.
Can you get it? Have to get her step stool out of the way. All right, thanks, Margie. It's good to be back at the Masonry Institute. What a great crowd, and I can, without reservation, say that this is the best looking crowd I've ever seen here. So if we had time, I'd like to take a selfie with each one of you, but fortunately we don't have time because I assume you came to hear about storm shelters, masonry storm shelters, and in particular, concrete masonry is what we're going to be talking about today. So real quick question, how many have seen or been through a tornado personally? Okay, a few. I think most of us know what a tornado is and the kind of how deadly they can be. So I don't have a lot of statistics for you or a lot of tornado videos to show you kicking off, but I did want to share this picture with you that my granddaughter did a few years ago. She had been thinking about recent tornadoes, and she drew this picture, and I was pretty impressed that she had the storm cell with the lightning amongst the storm cell and the funnel cloud. And then after looking at it 2 or 3 times, I noticed she actually has the grass being sucked up into the funnel cloud. And I thought that was pretty good for an 8-year-old. And then I've been going through some physical therapy on my leg, and the location I go to, they have the joke of the day. And so the other day they had this one. I don't mean to make light of tornadoes at all, but I thought, well, maybe this is a little good karma coming my way, knowing that I had to give this presentation here. So we have a lot to cover. I struggled with this presentation on what to leave out. I'll go as quickly as I can. We may run just a little bit long, but in case something goes unsaid that you would like to know about, I'll be around afterwards for some direct questions. Or you could send Margie an email and she could pass that along to me. I'll be glad to interact with you. But this is our outline we're going to go through today. These 4 points coincide with the 4 learning objectives that were approved for the presentation. First bullet point, why storm shelters? Well, I guess the first good reason is because the code says so. The 2018 IBC Section 423 now mandates storm shelters for certain uses, primarily Group E, which is your K through 12, and then also essential facilities that are located in what they call the 250 mile per hour tornado design wind speed zone. Which brings us to the second good reason, especially for us here in the St. Louis area, because if you look at that map with the tornado zone, the red zone there, St. Louis is shown with a star. So we're sort of like in the bullseye of that map. So it's pretty important stuff for us in this area. I did want to mention that Section 423 does not apply to the older critical emergency operations or the designated emergency shelters, which have been in the risk category list for a long, long time. And my understanding is that these are intended to provide extended shelter for people post-event. And so it's a little bit different ballgame for those, but those are designed per risk category 4. What we're going to be talking about is taking a structure up to resist tornadoes, or actually to resist the event. So how many architects do we have with us today? Oh boy. So I'll just apologize in the beginning here that most of our discussion today is going to be structurally related, in particular with the ICC 500, which gives us everything we need to know about designing and constructing storm shelters, focusing primarily on the things in Chapter 3, which are structural design. But you can see there are a number of chapters here where architectural aspects would fall into, and there's certainly a very important part of the overall storm shelter design and construction. The Institute has had some seminars related specifically to the architectural side of this discussion, and I'm sure they'll have some more in the future, but we're going to be focusing on the structural aspect. How many have designed a tornado shelter? A few. Okay, very good. So you're well aware of the increase in the wind loads that you encounter when you go from a normal building to a storm shelter level. But just to give you, for those of you who haven't done those calculations yet, here's just a quick example of a little building that I made up. And I calculated both the non-shelter wind loads and the shelter wind loads. And you can see the line across the bottom. The increase in the wind loads ranges from a factor of 2.3 up to 7.7 increase in the wind loads. And that's understandable because these tornadoes are very powerful and they put a lot of pressure on these buildings. The other thing you'll notice in the right-hand column for the shelters is the wall debris impact requirement. And so what the code is trying to do is account for the things that the tornado may have up in the air, throwing it around and maybe hitting our structure. And so the best gauge we have for that is the shooting a 15-pound 2x4 100 miles an hour at your wall system. And if it doesn't penetrate, then you are deemed to comply with providing the minimum amount of debris impact resistance. The good news is fully grouted CMU with a minimal amount of vertical reinforcement satisfies this test. And so it works very well for that. Second bullet point, what about concrete masonry shelters? Well, the obvious one is I'm a masonry guy, and you're sitting at the Masonry Institute listening to a masonry seminar. So we are going to talk about concrete masonry storm shelters. But what we did was when we first started seeing this mandate coming in the IBC, which I think the first time was the 2015 version, we said, well, there's going to be more projects that are going to require storm shelters in the future, especially schools. And if you think about the type of material you'd want to resist the high winds and the impact, a mass capacity material like concrete masonry is a good choice for that. And also, masonry has a long history of being on educational projects, so we're sort of on the job already. And so we felt like to take a concrete masonry building on a storm campus or a school campus to the storm shelter level should be pretty manageable. And so these were the thoughts we had internally, and we kind of like, well, how can we go about verifying some of those? So to quote a famous TV commercial, we started saying, "Where's the beef?" And so to that end, in the summer of 2021, right after COVID was kind of letting go of everybody, we brought some masonry designers in town, and we spent 2 days and we talked about what it would take to have concrete masonry serve for the wall systems of some storm shelters. And so we had a lot of discussion about requirements and detailing. We also brought in on the second day, second half of the second day, some of our local mason contractors and their foremen, superintendents, and we actually talked to them about going from a regular building level to a storm shelter, which was very helpful. And of course, no good meeting in St. Louis would be complete without going down to the Hill and having some Italian, so we did that as well. But the primary goal of the summit was to show that structural CMU can be used for tornado shelters, for common educational uses, and when used, what the related detailing might look like. So, sorry for the busy slide, but I wanted to give you kind of an idea of what the summit was like and what was determined during the summit and post-summit. There, which is the black bulleted points, then each one of these kind of has its own little backstory, but unfortunately I'm not going to have time to drill down onto that today. I'm just going to have to let those speak for themselves right now. If you have any questions on those, you can see me later or let me know by email. But these are the things that we predetermined that we were going to do when we developed some prototypes to study how this process would work. The green box represents the things that we gleaned from the ICC 500 we knew that would apply to the concrete masonry storm shelters. A lot of it has to do with the wind loading. And just a note on that, basically you calculate the wind load the same way you do for any other building, either using IBC, Chapter 16, or ASCE 7. Of course, the big difference is the wind speed goes way, way up. And that drives a lot of the wind pressures that you wind up with. In addition to that, the ICC 500 does impose some of the criteria for your calculations. They set those to certain values, as you can see there. So we came up with 3 prototypes, and what I'd like to do today is, as much as 60 minutes or an hour will let us, is to give you kind of the current status of each one of the 3 prototypes that we've been working on. The first one you see here, we're calling it the elementary classroom. It's sort of this shelter-in-place concept. You already have the students there, so if you can increase the capacity of that structure so that they can also shelter from the storm there, that might be a good approach. We're showing it as a standalone building just for convenience and clarity, but this could be part of a longer wing, or it also could connect to a bigger building as well. Now, based on and you can see the footprint and the height there, and based on the literature review that we did, we decided to go with hollow core planks. This is a precast concrete plank that would make the roof system. And by the time we put a concrete topping on that, we estimated our roof dead load could be as high as 100 PSF. And this is important when you're designing a tornado shelter because of the high uplifts that you encounter on the roof system. The more dead load you can have up on top and still be able to hold it up with your wall system will help you offset the uplift that can happen from these wind events. You can see the list there of the wind pressures that we calculated for the building, including the components and cladding, that's what we use for our out-of-plane loading, and you can see it's very high, 209 PSF. We anticipated using an 8-inch CMU, and we decided to go with an F'(M) of 2500, which should be quite easily doable in this area. And we also think in most parts of the country, you could get there without much problems. Wanted to point out, you'll notice that the openings by design are centered in standard control joint panels. As I said, this was by design. This is a good design procedure for all buildings, but especially helps a lot for the high wind loads that you encounter from the tornado in terms of the masonry around the openings. It gives you a lot more flexibility and how much you can reinforce what we call jam panels on each side of the openings, and also above the openings. You can connect those all together. Because the National Concrete Masonry Association says that if you have an opening within a standard control joint panel, and you're going to wrap that opening with reinforcement, you do not need control joints at the corner of the openings. And so we found that advantageous for this process. Now, we're not designing the roof per se, but we did give it some thought in terms of size and layout. Of course, the final design would have to be by the engineer of record and also the manufacturer of the roof system. But we did anticipate having 4-foot wide panels, and that we would span from the top of the slide down to the bottom. So those walls, top and bottom, would be what we're calling load-bearing walls, because the spans land on those walls, and then the other walls where the walls are parallel, we're calling those non-load-bearing. Now, all walls do have some vertical load on them, so that's a little bit of a misnomer, but just to keep us straight on which walls we're talking about, that's what we decided to do. Now, the top of wall detailing that we're working on, this is for the load-bearing walls. So this is where those hollow core panels are landing on our walls, and we're going to let those panels come on top of the wall, and we're going to connect those to the 8-inch masonry walls down below. Now, I'm showing you two details, one for the non-jam, in other words, the wall that's away from an opening, and also a wall that's in the vicinity of an opening. Really, the only difference here is that when we cross over to the jam wall, because of the extra load coming from the opening, we needed 2 bars per cell in that detail, whereas the other non-jam walls, we could get by with 1 bar per cell. You'll notice in the red boxes at the uplift, and one of the things you have to do when you're doing a storm shelter is definitely track the uplifts that you're getting from the roof system. You can see here we're estimating that these panels are going to bring, in the non-jam case, an uplift of 1,335 pounds per lineal foot along the top of the wall. And by the time you offset that with the weight of the wall, you still wind up with a little bit at the bottom of the wall. Okay. For the jam, it goes up a little bit, of course, again, because of the extra load that's coming from the missing masonry, so to speak. The approach that we decided to take on this one is to develop that uplift into the wall. So we're using those 2-foot by 2-foot number 5 reinforcing bars that are bent in an L shape to connect the hollow core down to the wall. And by the time you have the correct development length, we can dump that uplift into the wall. And then our assumption is that once that's dumped into the wall, the vertical bar or bars that's already there can then distribute that uplift down to the foundation. Now, that does mean that that bar that's in the wall has to do double tension duty. It has to withstand the tension coming from out of plane or in plane, and then also this extra tension that's coming from being developed in from the roof. But it did work in this case. We didn't overstretch those vertical bars. And then at the bottom, we'll have a dowel bar that's going to be lapped properly to deliver that uplift into the foundation. If you could not do that, if that uplift you were trying to develop into the wall exceeded what the vertical bars that are there can do, then you have to look at a more dedicated tension tie, which we will see on the next 2 prototypes. The 2 courses of bond beams underneath the bearing are there. They serve as the primary cords for the diaphragm action of the roof, and of course they also help tie the walls together at the bearing level. For the non-load bearing, you can see now that we're looking at the cores of the hollow core. We're again going to let those come over onto the wall. There's a lot less load coming from the roof on these walls, so you can see the uplift is a lot less. As a matter of fact, we wind up having none at the bottom of the wall. So we're using the same approach. We're going to develop that uplift into the wall and then let the vertical bars deliver it to the foundation, or to the dowel to the foundation. But in this case, because of the change in the format of the hollow core, we're counting on what I call a Z bar, which is a number 5 that goes down into the wall, up and over, and then into the page, or to the slide, if you will. And that'll all get grouted in together and connect the hollow core to the wall in that fashion. So I wanted to show you a little bit what we're finding out on the vertical and horizontal reinforcement. This is kind of a schematic. I hope you find it helpful. This is for the load-bearing walls. So the panels are landing on these walls. This would be for the north-south elevation if you're tracking that. The green bands represent the horizontal reinforcement in either a bond beam or bond beams or a beam over or under an opening. And so you can see at the top we have that one course bond beam with a number 4 bar. Coming down to the bearing bond beams, there's a 2 course. We're going to have 2 number 4s in each one of those courses. And then we decided to put a bar at the first course at the bottom of the wall. Some designers, some masonry designers feel this is kind of optional. The general feeling that I've seen is that it's good to have a horizontal bar in the vicinity of the dowels coming out of the foundation, either within the wall or at the top of the foundation itself. And we decided, since this wall is already fully grouted, it's not a big deal just to lay another bar in there and go ahead and take care of that. If I was doing a partially grouted building, I may or may not put that bar in there, but then you'd have to coordinate that with the foundation designer. Then the beam, we have beams over and under the 2 window openings there. Above, we have a 2-course beam with a number 4 bar in each course. And that beam is to deliver the vertical load to the sides and also the outer plane loads from the masonry above and the window below to the jambs on each side. And then we put a 1-course beam underneath the opening for good measure with 1 number 4 bar there. And you'll notice we've decided to extend that detailing over to cap the total jambs, if you will, on each side of the openings. And the jam width there, basically, we took advantage of what masonry was available and used that as our total jam. Just a quick reminder that all of these walls you're going to be seeing will have joint wire reinforcement for crack control. I'm just not showing it on these slides. It was on that first slide that we decided on during the summit. Here's the non-load bearing condition. We have 2 elevations this time because the door size changes. Oh, let me back up. I think I forgot to talk about the vertical reinforcement. Yes. So in the non-jam wall, which you can see, let me get my laser pointer going. There we go. Does that show? Yeah. This is a non-jam part of the wall. It's away from the opening. So from there to the control joint, we're anticipating needing a number 5 vertical bar 8 inches on center. So 1 bar in each cell. When you get into the area of the jam, because of the extra load, we felt we needed 2 number 5s, 8 inches on center. And then on the other side, we come back out to the number 5 at 8 inches on center. Looking at the non-load bearing, so here the panels, the hollow core panels are parallel to these walls. Most of this is the same, I believe. The beam over the double door went to a 4-course with 2 number 4s in each course because that's a little wider opening, more load coming to the jambs to get the vertical load and the outer plane load to those jambs. The jam width, we decided to go with a 6T assumption on the jambs. And the reason for that is it's kind of was done historically, but also because this is all going to be, there's no control joints at these openings, and so we felt like we could have this all work together as one item, so to speak, around the opening. So a 6T for an 8-inch unit would be 48 inches, or a 4-foot effective jam is what we're counting on there. In this case, because there is more load, the jam reinforcement went up to 2 number 6s, 8 inches on center, rather than 2 number 5s. But on the lower elevation there, where we're back to a smaller opening, it did go back to 2 number 5s. So the second prototype is what we're calling a middle school gym. We wanted to be big enough to have a basketball court, so it could be used to play basketball, or it could be used just as a general activities room. You can see the footprint there. The overall height of the building is now 30 feet. And we're starting to track the ceiling height because if you play volleyball or something in there, you need that extra height to do that. For this building, we had seen in the literature where precast double T concrete roof system was used a lot. So we decided to go with that, and we felt like time we put a concrete topping on there, we could be at 100 pounds per square foot dead load again. Again, you can see the wind loads that we came up with for the building based on its size and shape. And we decided to go with a 12-inch unit, but holding the F'(M) at 2,500. Moving on to the roof, again, we're not doing the final design here, but this is what we're envisioning. 8-foot wide double T panels. You can see that by the solid lines. The dotted lines represent those T's, the stems that come down 4 foot on center. And yeah, so we were again expecting to span from the top to the bottom. So we have load bearing walls up here and non-load bearing on the sides. So the top of wall detailing for this system that we're working on, this works also for jam and non-jams. This is for load bearing jams and non-jams. The reason the same detail works is whether it's a jam or not, it needed 2 bars per cell. And so really the same detail works. The only thing that will be changing is the vertical bar size. You'll note the uplift box there. We're estimating that each double T stem, when it lands on our wall, will be bringing approximately 15,500 pounds of uplift. And that then became more than what we could handle by dumping it into the wall and expecting the vertical bars that are already there doing something else to be able to get that uplift down to the bottom. So we had to go with a dedicated tension tie. You can see that called out down here at the bottom. So at every double T bearing location, there's a bar that's going to be welded to the bearing plate in the masonry that will be continuous all the way down to the foundation. And it's not counted on for out of plane design or in plane design. It's only there to be engaged if you get net uplift coming from the roof system, which you definitely do in this case. So you can see we're letting the double T, and we're going to come over and we're going to share the 12-inch wall below. And we decided, we looked at how we're going to enclose the ends of the double T's because they're not solid generally, is we decided to go with a 6-inch closure wall. And you can see that goes from the top of the bearing all the way up to the top of the wall. The purpose of the closure wall does give us that impact resistance. It does close off the ends of the double T's. But we're also expecting it to help deliver the shear coming from the diaphragm when the load is into the slide, if you will, to work as a little shear wall that'll get that diaphragm load down to the wall below, where then we can distribute that down to the foundation. So that little closure wall on top was checked as a pin out of plane and also a cantilevered little shear wall to help out with the shear coming from the diaphragm. And you can see there's a bent bar anchor there that's going to be help all that happen. Plus the reinforcement comes up from the bottom to help with the cantilevering of that wall. Again, we have 2 bond beams below the bearing. In this case, they not only serve as the diaphragm cords, but we also check those to provide support to the top of the wall between the double T locations, right? Now the double T's in this case were spacing, the stems are spaced 4 foot on center, which you could argue could still be considered a uniform load, but we were a little bit worried about that in a tornado level design. So we checked these bond beams in addition to being the diaphragm cords, also serving as the support for the top of the walls in between the bearing locations. Once you get back to the bearing location, then you'll get that anchorage from the double T system and everything to keep the wall in place. Now, this red note here, we're a little unsure yet what to do about this. It seems to us that when you go into net uplift on the roof, then the bottom edge of your roof system goes into compression. That means the bottom edge of these stems go into compression. Normally, they're almost always tension when you're talking about vertical download. And we looked through the literature, we asked some precast people. I actually attended a couple webinars, could not get a good answer on how this is typically done for double T's. So what we're doing right now is just putting a note saying compression brace the bottom edge of the stem or the manufacturer. If they have another way of doing that, to keep that stem from buckling or crackling out of plane, then you could do whatever they say, I suppose. But we just wanted to make sure that that gets addressed. Okay. So here's the non-load bearing condition. You can now see the stem of the double T. We're going to bring that over to the wall and again connect it to the wall. Now, interesting enough, these non-load bearing walls have to work harder because their overall bearing height has gone up to the top of the diaphragm now rather than down here where the bearing location was. We did decide to run those two bond beams around anyway, just for good measure, because we want to make sure they were in on the load bearing side, so make sure they get built around there. We have less uplift, and so in this case, this is another case where we're going to develop that uplift into the wall and let the vertical bars that are already there develop that uplift down to the foundation. So a tension tie is not needed on the non-load bearing walls. We also don't need the closure wall because we're going to run the 12-inch unit all the way up in this case. So looking at the horizontal and vertical reinforcement, the same kind of pattern we saw before. The green is for your bond beams or your beams over and below windows. You can see the jambs there. We're using a 6T again for the jamb width. So that would be a 12-inch unit. Would be 6 feet for that. And so that's what we're counting on for the jamb width. The non-jam vertical reinforcement you can see is 2 number 5s, 8 inches on center. And then when you get into jam, that would go to 2 number 6s. And then this masonry below the window needs a little bit of help. So we're putting a number 6 bar, 8 inches on center there. Then we go back to the 2 number 5s. And then again, 2 number 5s on this panel over on the far right. This white panel, just the panel to the left, it would be the same as the panel to the left. I just didn't bother to color code it. Notice the tension tie there all across this elevation. That would be at each double T stem bearing location. And that would be a number 6 vertical bar going all the way down to the foundation. The rest of the horizontal reinforcement is pretty standard, what we've already seen on the top of wall detailing. I did want to talk about the closure wall. You can see that's up here, the 6-inch closure wall. We're counting on a number 5 vertical, 32 inches on center there, and the bond beams called out here agree with that top of wall detailing that we saw. But we had a decision to make where the 6-inch wants to become a 12-inch. And so what we decided to do is let that 6-inch unit just die into the 12-inch unit. So that's what the little white here you're seeing is a 12-inch unit from the side walls coming through. And I've got some details that may help with that. First of all, I'm sure you know this already, but if you have a 12-inch unit on a building, the mason has to do a little bit of magic at the corners and to make the coursing or the bonding work out. And so typically what they do is go use an 8-inch unit plus a little piece of solid there so that when they turn the corner, they're right back on the bonding, for the running bond of the unit. So nothing new there. I just wanted to point that out. But when we had that 6-inch at the top, we decided to let that 12-inch unit come through, die the 6-inch unit into it. We'll probably put some control joints there to give a little movement if we need to, so we don't get a lot of cracking there. And you can see the 12-inch bearing line below where the double T's will be coming in to this system. And then notice to stay on bonding again, the mason will have to do a little piece of a solid and then take a unit, cut it down to 12 inches. So if you look at that in elevation, you have that 12-inch to 12-inch corner down here. And then above the 26-foot bearing line, you have the 12-inch units showing with the control joint, and then whatever the mason needs to do there to get back on coursing. May not be the best detail architecturally, but we thought for now structurally that's what we would go with to do that transition. The non-load bearing wall reinforcement schematic there, very much what we just saw. Still 2 number 6s, 8 inches on center. When we get to the jambs, because of the bigger door, the size of the opening, and because this wall spans taller than the other walls, we had to go to two number 8s, 8 inches on center for the jamb reinforcement. And then that beam over the opening, that beam over the opening is a 3-course beam with a number 6 horizontal bar, top and bottom, to make that system work out. We're doing a number 6 vertical bar, 8 inches on center over the opening. And again, no tension ties needed on these elevations for the east or the west. So also no closure wall needed. All right, so here's the third one. It's the largest one. Look, what we're calling perhaps a high school gymnasium, where you enclose the basketball court, but you also have some space for some bleachers on one side. And so this 104 foot by 104 foot is the size of this building, 38 foot tall with a ceiling height of 30 feet. We had seen in the literature where some double T's are used for this size span for storm shelters, but to be different, we wanted to see what it would be like if you tried a structural steel roof system, just to see what that detailing, how that would come out. Now, the first thing you're faced with if you do that is that it's going to be a lighter system overall. Even if you put a concrete topping on it, we thought we could only count on 60 pounds per square foot of dead load. So not only is the building going to have more uplift due to its size and shape, but also the fact that it's going to have a little less load on the dead load on the top. And you can see those wind loads there that we calculated. We wanted to stay at a 12-inch unit, but we thought we might go up to an F'(M) of 3,000. And this is still within range of most areas in the country. Certainly here in the St. Louis area, you can do an F'(M) 3,000 quite easily. So a little bit of a busy slide because of the size of the building, but basically, first of all, I wanted to thank Dr. Mark McGinley from the University of Louisville. He did the preliminary schematic design on the structural steel roof that you see here. And basically what it is an 80-inch deep joist, main joist, that's spaced 56 inches on center. You can see that we're anticipating having some double joists to straddle the door opening, because each one of these joists will need a tension tie at the bearing, and we didn't want that to happen over a door opening. So we're going to put doubles on each side, or anticipate putting doubles on each side. We may put another joist in between the two doubles just to pick up the roof load, but we're not counting on it that much for uplift. You'll also notice that we have turned the joist at the ends of the building with what we're calling sub-joists that are 80 inches deep and 56 inches long. One of the reasons we did that is that it allows us to keep the bearing height for the system the same all the way around the building, right, as you'll see in the top of wall detailing. We're also anticipating that you could put 80-inch deep brace frames between the ends, in between the main joists at the ends, and also in between the sub-joists to provide more lateral stability for the system overall. Top of wall detailing, this will be for both the load bearing and the non-load bearing, because the top of the wall bearing height remains the same. It also works for jam and non-jam, because we again need 2 bars per cell either way. It's just the size of the bar will change. And we're letting the main joist or the sub-joist come onto the wall. And again, we're using that 6-inch closure wall as we did with the second prototype. A little bit taller, but we were able to still get it to work, serving those same purposes. In other words, providing the closure to the system for impact, but also help dumping the shear from the diaphragm down to the wall below. Now, we also anticipate that this brace frame in between could also help do that, but that would depend on the final design and the engineer of record, how they wanted to approach that. The 2 bond beams underneath the bearing, again, serve as diaphragm cords, but also they've been checked to support the top of the wall in between the bearing location, which is 56 inches on center. And the uplift here, as you can see, for each main joist, we're anticipating 40,000 pounds of uplift coming from each one of these main joists. Now, the sub-joists that are turned the other way would be much less. So the key is for those main joists, and again, we're going to do a tension tie, as you can see right here, that would go from the bearing point all the way down to the foundation. See if there's anything I missed. Okay, so again, the bottom edge of the system would need to be braced because it will be going into net uplift. Now, oh yeah, for the subjoist, that uplift, we're going to distribute that down into the wall, and you can see down here in the note, for when it's a tension bar, we need a number 8 bar down to the foundation. For the subjoist, we need a number 6 bar, 48 inches long, down into the wall to distribute that uplift down into the rest of the wall. Okay, horizontal and vertical reinforcement, color coding is the same. The non-jam, we're again at 2 number 6s at 8 inches on center, going to 2 number 8s in the jam location, which is 6 feet wide. Looking at this, you could extend this detailing over to the control joint if you wanted to. We decided not to show it that way for now. And then back to the 2 number 6s vertical bars. We have a 6-course beam over this opening due to the size of the opening and the span and the out-of-plane load coming on the building. 6 courses of masonry with a 2 number 7s at the top course and the bottom course. So that's about a 4-foot deep beam there. Closure wall works pretty much the same as before, except we're not having to make that transition. We're turning a 6-inch unit around the top of the building, so that gets, we felt that was a lot easier that way. Okay, that was load bearing. This is non-load bearing, where we have the little window opening, 2 number 6s again, and the non-jam. Now we're only at 2 number 7s for the jams. And the top of the wall still works the same. Tension tie not needed here because we're able to distribute that uplift from those smaller subjoists down into the wall. All right. Now, I know that was really quick, but that's what we have so far on these 3 prototypes. And the good news is so far it's showing us that we can use reinforced concrete masonry for storm shelters on some of these common educational uses on projects. And we think it's actually should be a system worth considering on those types of projects. What I'd like to do for the time we have left is share with you some of the other things related to the storm shelters. First of all, some comparisons we've been making shelter versus non-shelter. At the top here, we're looking at primarily structural, where we have the 3 prototypes listed. You can see the change in the CMU. Actually, there's not much of a change really, except on the second one. The big change is that the non-shelter can be done partial grouting, okay? The storm shelter, even if you could get it to work partial grouting, you would still need to fully grout for the impact resistance. So that's just a given on storm shelters. Looking at what I call the base reinforcement, in other words, the non-jam reinforcement, you can see for the shelter on the smallest one, was the 1 number 5 at 8 inches on center. We could go to a number 4 at 32 inches on center if it was a non-shelter. For the second one, 2 number 5s, every cell could be a number 5 every 2 feet. And then on the larger one, 2 number 6s, 8 inches on center, could be a number 6 at 16 inches on center. Then once we kind of took a look at that, we also wanted to get a feeling for what is the cost change and schedule change going from a non-shelter to a shelter. So we ran some figures on that, and you can see those listed here, the non-shelter total cost and then the shelter total cost. Now keep in mind, all we've done is this masonry subcontractor installed price, okay, for the St. Louis area. It doesn't include GC markup or anything else you might pile onto a project like this. It also doesn't include the roof system or the foundation changes you'd have to go through. We're just strictly interested in the changes in the walls. So you can see the increase, not much on the first one, and then it gets a little bigger for each one on the next 2. When we started, we were guessing a cost increase to go to the shelter level of about 33%. And we saw that actually on a couple of them. Now the middle one, we're not exactly sure what's going on there. We're still looking at it. We think it has to do with the percentage of 6-inch units to the 12-inch units. The bigger building has a larger percentage of 6-inch units compared to the 12-inch units than the smaller gymnasium, which only has 6-inch units on 2 walls. And so far, that seems to be the thing driving the little extra cost difference there, but we're going to keep looking at that as we go along. But in any event, if you average all 3 of these, you get 34.8%, which is coming out pretty close to what we were guessing. And we feel that that is, worthwhile to say that we feel that that's pretty economical to get to that protection you need in the storm shelter. Now, schedule's a little tough to do because masons can use different crew sizes at different times. We decided to go with one basic standard crew. Greg, do you remember what it was, like 3 and 2 or 4 and?
On the smaller one, 8-5.
Okay, so what the mason usually does, mason contractors, they decide how many mason tenders they need for the number of masons they're going to have in the crew, and that's how they set the crew size. So keeping that the same, you can see the change in the schedule. The first smaller one, not that big of a change really anticipated in the schedule because it's still within kind of normal construction ranges, if you will, for the shelter level. But for the 2 larger ones, you can expect a couple more weeks here and there to get to that level, to get that extra reinforcement in and the extra grouting in. Big thanks to Greg with the Masonry Structural Coalition for running those numbers in conjunction with Luke Siebert, one of the owners over there at High Camp Masonry. So we appreciate them working through that. The last bulletin point was what about seismic? And what I decided to do here is seismic is still important. You have to, even if you still have to design these storm shelters for seismic, even if you're in a low seismic area. But what I decided to do for the 3 prototypes is to show you the base shear coming from the seismic compared to the wind, also the out-of-plane wind load compared to the seismic. And what you'll notice for our 3 prototypes, and since we're pretending that these buildings set right here where you're setting, based on the seismicity, you can see that the wind base shear is always controlled. So your in-plane design is going to be controlled by wind, and your out-of-plane is very much controlled. It really drives the bus on these out-of-plane designs. But you might say, well, what if you're somewhere where the seismicity is higher? So I did the same thing for Cape Girardeau, where I assumed they would be a seismic design category D, which drives up the seismic forces. And you can see for these fully reinforced larger walls that the seismic base shear starts to compete and to take over the wind, but not by much, okay? And then if you look at the out-of-plane, you're still, 3 times more on the wind load. So typically what happens is you size everything for the out-of-plane wind. What we're finding is by the time you do that, you have more than you need for the in-plane shear walls, especially these buildings these prototypes that have longer concrete masonry shear walls. So it's really still the wind that's going to kind of govern your design there. Just a few other things. Lap splices. We do intend to have a full table of lap splicing for these prototypes. We are using the lap splice equation from TMS 402, Chapter 6. We are not counting on the IBC 72 bar diameter cap that it places on this equation. We just thought that wasn't prudent to do for these storm shelters. And also if the calculated lap splice was less than 48 bar diameters, we're thinking about increasing the lap splice to 48, because most of our masons are still very familiar with that old 48 bar diameter rule for lap splices. Now, using this equation, if you have a big bar that's offset toward the outside face of the wall, you're going to get some long lap lengths. As a matter of fact, for the number 8 bar that we saw in some of the buildings, the lap length is 117 inches, which just doesn't make sense anymore. So what we're probably going to do is recommend that for a number 7 and number 8 bars is that you go to a mechanical coupler instead of trying to lap those bars to do your splicing. They're becoming more popular, more projects are using them, and we just think it's probably the way to go for this. And then the foundation and the foundation doweling, we're not doing any of that design, but we probably will give some guidance for what the wall needs from the doweling. So the first prototype there, the smaller one, we're anticipating a dowel 24 inches on center coming out of the foundation, and we'll probably want the size and number of that to equal what the wall is doing above. And then we would want that dowel extended into the wall based on the lap splice table that we come up with. Now the other two, the larger two, well, let's take a look at the middle one first. We're anticipating a number 6 dowel needed for the wall, 24 inches on center, between and at tension tie locations. And we expect that dowel to extend up into the wall 4 foot on center. And that way we can give the wall what it needs in terms of doweling, but also give that tension tie what it needs to deliver that uplift load to the foundation. For the larger one with the larger uplifts, away from the tension tie, we're still going with the number 6 at 2 foot on center. We extend that up into the wall 48 inches, but when you have a number 8 tension tie, we're probably going to recommend that that's done with a coupler. So there's going to be a receiving coupler in the top of the foundation, and either a threaded bar or some other kind of coupler where you can connect that tension tie into the foundation and get that load down into the ground, hopefully eventually. Masonry veneer. We do expect many of these storm shelters, if they're concrete masonry, to have masonry veneer on them, anchored veneer with an insulated cavity. That's a great way to address the overall thermal performance and moisture protection of the walls, I guess in between tornadoes, if you will. But our assumption was to assume that there's no veneer there or it's been lost to the tornado. And the reason for that is if you design your anchored veneer per chapter 13 of TMS 402, that detailing, prescriptive detailing, is only good for up to 55 pounds per square foot at the most. And we're well exceeding that with these out of plane wind loads. So the moral of the story is if you want to have a veneer on your storm shelter and you want it to stay in place during the storm, then you're going to have to engineer that whole veneer system as well, so that it does have enough anchorage to stay on the wall. Otherwise, it's going to become potential missiles for the tornado, which is maybe something we can't avoid too much at the end of the day anyway. The other thing to keep in mind, if you do add veneer to the exterior of the walls, it will add to the seismic base shear and to the seismic out of plane load because of that extra weight that you just have to take into account. The last one here is quality assurance, quality control. I just wanted to point out that the same care and effort we take on all of our structural projects apply, of course, to these storm shelters. You have to have a quality assurance plan. You have to have special inspections. In this case, for the high winds, you're going to have structural observations. You need the statement of special inspections, pinpointing the possible list of inspections that are going to be applied to that given storm shelter. And then in addition, the ICC 500 requires in almost all cases an independent peer review on your design for the storm shelter. So once you're done with your design, you have to send it to somebody independent, let them go through everything, make comments, write a report, and then that gets submitted along when you do your final approval with the building authority. The last one there is we had heard from some of our precast competitors were saying you don't want to use concrete masonry for storm shelters because you have way too many special inspections. And we take exception with that. Every structural system used on a building has to have special inspections. And if part of it is fabricated off-site, it still has to be specially inspected. And then when it is installed, when it's craned in place and when it's welded, it's 4-point connections, if it's a precast wall, those become very, very important special inspections. So I'm sorry if that sounds a little crusty, but I'm retired now, so that's okay. I always say special inspections are our friends all the way around. Well, that brings us to the end of what I have for you today. So much more could be said. As a matter of fact, looking at what's next, we hope to keep finalizing our prototypes and getting them vetted and reviewed. We're also working on some Revit files for the floor plans and the wall elevations and the details, if people may find that helpful. We also intend to finish with a white paper or a final report on the whole process, which would be available to everyone, and then more and more PowerPoints like we've been doing today. I just quickly wanted to thank the designers who came for the storm shelter. You'll recognize these names. They've been presenters here on multiple times. David Biggs out of New York. He'll be here next week. Mark McGinley, University of Louisville. Jason Thompson, who at the time was with National Concrete Masonry Association. Scott Walkowitz out of Michigan, who is the current TMS 402-602 chair. So we had some pretty good heavy hitters from the masonry industry work through this. Also some great industry and staff support. David Gillick, the Mason Contractors. Greg Bryant, of course, MSC. Margie Gagne did a lot of work. Thank you, Margie. And then also Mark Wilhelms from the Midwest Block and Brick. He attended the summit, offered a lot of great input. Many of you work with Mark. He's a wealth of information, so we really appreciate what he was able to do. And one final thing, Greg Bryant is a great contact if you'd like to know more about concrete masonry storm shelters. He and I talk quite often, and we can interact with you as much as you need. So with that, I want to say thanks for attending, and it's been great to be back with you.
Thank you, Darrell. See if I have any questions, or if you'd like to come up and talk to Darrell afterwards, that works as well.
I might sit down on you, but
Let me go to the next slide.
I'll be glad to. Yes.
I didn't see a address on concentration and equalization.
Yeah, that was in that busy slide that had everything that we decided. What he's asking is the internal pressure coefficient. And so if you have an enclosed building, you increase your loads by a factor of 0.18. If you have a partially enclosed or fully not enclosed, then it goes up to 0.55. We decided to take the FEMA recommendation is to do the 5.55 always. So we decided to do that. Now, if you wanted to stay at 0.18, you have to jump through some pretty significant hoops on your HVAC system to make sure you balance out that pressure, that you don't reach the 0.55. And we just felt that was a little bit more than we wanted to do on this structural study. But that's a great question. I'm glad you asked that. Yes, Leonard.
For IBC 514, you have approved live load of 100 pounds per square foot?
Yes, that is the requirement of ICC 500 of 100 pounds per square foot live load. The reason for that is that accounts for anything that might get thrown up on top of the roof during a tornado, like a school bus. And we've seen pictures like that. You probably have too. The other thing I didn't mention is the ICC 500 also requires you to look around your project. If you have radio towers or other things that might fall down on your building, you have to include that load in your design. Now, they don't tell you how to do that, but they say you need to look around, and it makes sense, right? If that radio tower happens to fall on that building, then we need to be able to withstand that too. Or tell them to move the tower. Yes, great question.
With all the heavy reinforcement of walls, what's the point of the control?
Another great question. The question was, with all the heavy reinforcement in the walls, why do we need control joints? For our prototypes, since we're seismic design category C, we have no horizontal reinforcement in the field of the wall. So to be able to not have control joints in your walls, you have to have, I think, a number 5 bar at 16 inches on center, horizontally. And our friends out in California do that all the time. So a lot of times they don't put control joints in their buildings. But we felt because we were exposing the buildings to a lower seismicity, where we had no horizontal reinforcement other than the joint reinforcement, that we needed to go with control joints. If you wanted to beef up the horizontal reinforcement, you could eliminate those if that was important to you. Another great question.